Okay, so let's start. All right, so last time I started to introduce the theory of horizontal distributions, and what we want to aim for is actually connections. And so let's see, what's the connection? So remember, so the setup is as follows. So we have a bundle over a manifold. So let F dot be a C bundle with model fiber F over or on manifold M. C infinity pseudo category. And then I talked about horizontal distributions. So the situation is like this schematically. Here we have the base manifold M. Here we have the total space E of our bundle. We have the projection map. And then we at each point X in M, we have the corresponding fiber Fx. And now at each point of the fiber, little e, we have the tangent space to the fiber. So that's a tangent space to the fiber as a subspace of E. And the horizontal distribution associates to each point E an algebraic complement. And we call this HE. So that the direct sum of HE and this space gives the tangent space of the whole tangent of the total space. So we call it the tangent space to the fiber, we call it the vertical space, and HE will be called the horizontal space. So we have these distributions, and then I talked about parallel transport. Once we have that, we obtain parallel transport, and essentially this is given as follows. So if I have a curve joining 2 points in my manifold M, a curve connecting them, then what I do, I look at the fibers of these 2 endpoints, and then I have these horizontal spaces, and this curve can then be lifted in such a way that it's always tangential to the horizontal space. So any point here, E, I will look at the curve tangential to this horizontal space, and eventually, if the solution of this integral curve exists long enough, I will hit the fiber at the end point of the curve. And this mapping the point E here to the point, this intersection point there, that's the power transport. I formulated it in terms of pullbacks of the bundles along the curve to get something over an interval, but nevertheless, so that's what's happening. There may be the problem that these curves, these horizontal lifts, do not exist all the way up to hitting the other fiber, but we will always assume that this problem does not arise. For example, if the fibers of the print of this fiber bundle are compact, then this problem will never arise. All right, and now I can define what connection is, definition. This is such a horizontal distribution. H is called a C connection, or a connection of this bundle F. I just want to emphasize the C once more. If the following holds, if parallel transport is defined along all curves, for instance, if the fiber is compact, and this is not a condition, and more importantly, the parallel transport along such a curve. So this is a diffeomorphism from the fiber of CT1 to the fiber of CT2, because the inverse is given by just going back the same curve, going it backwards. Then this is a diffeomorphism, but it should not be an arbitrary diffeomorphism, and this is where this structure category comes in. It should be an isomorphism in that category. From fiber at CT1 to fiber at CT2. will see what this means in concrete examples. Okay, so but that's certainly a very natural definition. So that's a connection. And now you may still wonder how this is related to the theory of connections as you know it in terms of Laplace. And so let's discuss this now. So definition. So suppose we have such a connection. So H is such a connection. Then I can define the corresponding covariant derivative. So let H be a C connection. Now what should the covariant derivative do? So it takes a section of the bundle and somehow differentiates it, right? And in a direction, let's say. And how do we do that? So let S be a section of my bundle. I have not introduced a notation for sections yet. So I need a 1 times differentiable section if I want to differentiate it. And the notation I'm going to use for sections is C1 base manifold with values in my bundle. So that's what I mean by sections. So it's not the same thing as maps from M to the total space because we have the section condition, right? So that's what I mean. So let's S be a C1 differentiable section of my bundle. And X should be a tangent vector of my base manifold at some point P. Then I want to define the covariant derivative nabla xs. So I want to differentiate S at the point P in direction X. How do I define that? There is a way to differentiate sections by just taking the differential of S at the point P and insert the vector X to it. What does this give me? Well, S is a map from the base manifold to the total space. And if I differentiate that and insert a tangent vector of M, then I get some tangent vector on the total space. But I don't want some, and this does not, depend in any way on my H, on my horizontal distribution. But what I now do, I take this vector, this tangent vector to the total space, and project it to the vertical part. So I apply this projection onto the vertical part to it. So this will then give me a vertical vector. And that's the covariant derivative. So then nabla xs is called covariant derivative of the section S in direction X. Okay. All right. So that's the definition. Let's see. If S is a section and X is a vector field, so let's say for S, let's say a smooth section for simplicity, and X a vector field, which would mean it's a smooth section of the tangent bundle. So if I do this at every point, then I get another section, but a section of what? So let's see. So this is a section in which bundle? Yeah, what's the bundle? Any ideas? Yeah, but the vertical bundle is a bundle over E, not over M. So it should be a bundle over M, right? Yes, that's the correct. S star V. That's what it is. Right? Because at each point of the manifold, this is an element of the vertical space with base point S of P. So in other words, it's an element of the pullback bundle along S at the point P, as it should be. Exactly, that's what we have. And if we leave this slot open, we could also talk about nabla as a section on the manifold, in such a way that I can contract it with a vector field to obtain this section. So, and then I would consider this as a section of this bundle, but then there's an additional slot in which I can put my vector field, so that should then be in the dual bundle of the tangent bundle, so that's F140, so it's a section in this tensor product. So that if I insert X, I contract with this part to obtain a section. Alright, so that's what we have. So this works in all generality for any bundles. And now let's try to interpret this condition or this definition of a covariant derivative a bit more, understand it better. So the first remark is the following thing. So concerning this projection, and since you asked, I make this more explicit. So if we project, so let's take the complementary projection, which is the projection onto the horizontal space. I claim that if I apply this to some vector, or we call it y, because x was a tangent vector on M, and this should be a tangent vector on the total space, so let me call it y. So I can express this as saying, take y, project it down to the base manifold, and then take its horizontal lift. And why is that? Let's check that. So namely, so it's by linearity, it's sufficient to check this on vertical vectors and on horizontal vectors. So for vertical vectors, so meaning it's tangential to fiber. So what happens then in this case? Let's say the right hand side, d pi of y is what? 0. I explicitly stated this last time, that the vertical space is the kernel of the projection differential. So that is 0. And then if I lift it horizontally, of course, I get 0. And if I take a vertical vector and project it to its horizontal part, then of course that's also 0. So for vertical vectors, it's okay. And for horizontal vectors, let's see. Well, I have d pi of y, horizontal lift. So now we really have to remember what the definition of horizontal lift. So how did we define the horizontal lift? We were saying we take the differential of the projection, restrict horizontal vectors, and take its inverse. And this has now to be applied. So that's the definition of this horizontal lift. And now let's apply this to d pi y. And since y is horizontal, so this is exactly the inverse of this map. So I get y, which is of course the same thing as the projection onto the horizontal part of this horizontal vector. So that's also good. So we have this characterization or formula for the horizontal projection. Now, if we use this to write down the covariant derivative once more, so here's the definition. Here I have the vertical projection of the usual differential. So I'm leaving out the foot point to make the notation to avoid it, to make it too clumsy. So in any case, so that's the orthogonal projection to the horizontal projection. So let me write this as ds of x minus the horizontal part. But now we have just computed this formula for the horizontal projection. So this gives me ds of x minus, and I can insert the projection of what I'm having, what I have here, and then take its horizontal lift. So this is just this formula with y equal ds of x. And let's see what we have here. So the first thing is ds of x minus, and now I have d pi followed by ds. This is to be understood like this. I have d pi followed by ds, which is, by the chain rule, d of pi composed with s applied to x, and then I take the horizontal lift. What is pi composed with s? Here we use the section property. Section is just defined as something where this is the identity of the base manifold. Right, so this is identity on M, and so the differential of it is also the identity. So this whole thing just gives me x to the h. It's ds of x minus the horizontal lift of x itself. So that would be an alternative formula for this covariant derivative. And here you see the dependence on the horizontal distribution a bit better, because how you lift horizontally depends on the choice of h. All right, good. Well, some properties that these covariant derivatives have in full generality, namely, by the very definition, we see that this covariant derivative is certainly linear in x, right? Because this is a linear map and that's also a linear map. So, in fact, it's function linear. So, namely, if we have a vector field x1 and a function f1 plus a vector field x2 and a function f2, and insert this, then we get a U section. And since this is evaluated pointwise, and since this is linear in the x argument, pointwise, I can first of all take this apart. So this will be, okay, let me write down. So this is pi v ds applied to f1 x1 plus f2 x2. And so I can drag the function out and also take the sum part. So that's f1 pi v of ds of x1 plus f2 times pi v of s of x2. So in other words, this is the same as f1 times nabla x1s plus f2 nabla x2s. And don't forget that this is valid for all bundles, not just for vector bundles, for all fiber bundles. And the reason why this works, and the reason why this makes sense at all, is the fact that these covariant derivatives take their values in a vector bundle. They are sections of a vector bundle, even if the original bundle is not a vector bundle. Right? Otherwise, these formulas would not make sense. So, but asking for linearity in S is not meaningful, because S is a section in a fiber bundle, and then in general, there is no such thing as linear combinations. Okay. All right, good. But I'll come back to the situation when we are actually starting with a vector bundle, when linearity in S would make sense, and see what will happen then. But we will come to this in a moment. All right, good. Now, let me give yet another interpretation of the covariant derivative. And relate it directly to power transport. So, Emma. So let C from some interval I to M be a smooth curve with a derivative at 0, let's say, being a vector x. And now I want to express the covariant derivative of a section in direction x in terms of this curve. And indeed, then The covariant derivative of s in direction x can be written as follows. So what I'm taking is the following thing. I take my section and evaluate it at the curve point c of t. And then I get some element in the corresponding fiber over c of t. But I want to have a proper derivative somehow, so I need to put things in a fixed fiber. And for this, I use transport. And I can consider this as a S composed with C is actually a section of the pullback of the bundle along C. So I can do the foreign transport, I can transport from T to 0. And then I get something in the, for each T, I get something in the fiber over C of 0. So I get a curve in the fiber over C of 0, and I can take its derivative. And then I get a tangent vector to that fiber, so I get a vertical vector, so that looks good. And indeed, this formula is correct. This way, parallel transport can be used to give a formula for the covariant derivative. So we have to prove that, of course. Well, okay. So really, we are working on the pullback bundle over the interval along the curve C. So C, S composed with C is actually a section of pullback bundle along the curve C, because for each T you associate an element in the fiber over C of T, which is the corresponding fiber of the pullback bundle at T. And also remember that parallel transport was also defined by using this pullback, so it's actually quite convenient at this point. In order to see this formula, consider the following map Q. So it's defined on the total space of the pullback bundle. So that's sitting over the interval I. The bundle sitting over the interval I. And I'm mapping everything to the fiber that I'm interested in, namely the fiber f of c at 0, 0, which is the same thing as the pullback fiber at 0, by definition. And what is the map? Well, an element E tilde gets mapped to, well, then let's take E tilde. So that's some element in the total space, and I just use the parallel transport to transport it into this correct fiber. So I'm applying parallel transport. I want to end up at 0, and well, here this is sitting somewhere. So let's see. Let me call it pi tilde of E tilde, where pi tilde is the projection of the pullback. So I just take the element and parallel transport it to that fiber. So this gives me a map of the total from the total space to this particular fiber. Remember, when talking about connections, I was assuming that parallel transport always exists, so there's no problem with existence. Okay, now when I restrict Q to this fiber as a subset of the total space, then I get the identity of that fiber, right? Because parallel transport from the fiber to itself, so P00 is just the identity. So it's a map from the total space to the fiber, which on the fiber doesn't do anything, it's just the identity. Okay, good. So let's differentiate this map to get something on the tangent spaces. So then the differential of Q at some point E restricted to the tangent space of the fiber, which is the vertical space of the pullback bundle at t equals 0. So since this is just differentiating the identity, I get the identity of of that tangent space, this vertical space. So this is this linear map, or this linear map has this property. And what does it do on the complement on horizontal vectors? When I restricted the complement to the horizontal space of the pullback bundle, right? I explained last time how to pull back the horizontal space, so I get this horizontal space. What does it do there? Any ideas? Indeed, so if I have a horizontal vector, I can represent it by a curve which is horizontal, but that means it's parallel, and so that means if I apply this map Q, if I apply the map Q, I get a constant curve in the phi, but if I differentiate that, then I get 0. So this gives me 0. In other words, this differential of Q at the point B tilde is nothing but, well, it's this projection onto the vertical space. Right? Good, that's good, because this sets up the relation to the original definition of covariant derivative that I have here. So now, let's see what happens. So if I look at the right-hand side of this expression here, t equals 0. So what is this actually now? This is the differential of, now this was the map Q as I defined it, and I apply it to the composition of S and C at t equals 0, right? And so by the chain rule, this is the differential of Q at the point S of C of 0 applied to the derivative of this. At t equals 0. But we have just seen that this differential is nothing but the vertical projection, and the differential of this will give me ds of the derivative of c at 0, and the derivative of c at 0 is x. So I obtained exactly the formula I used to define the covariant derivative. So this is lambda xs, and this proves the lemma. Good. All right, and that's useful to have a characterization in terms of parallel transport, because so far we have not used this fact, right? So we have not made use of this fact because this is a condition on parallel transport. And now let's see what this means in particular cases for our covariant derivative. This one we could define for any distribution, that's true. But then we would be unable to relate or to impose conditions on H to relate it to the category C. And we will exactly, so for this characterization we need it. And this is exactly what I want to use now in order to see what this means. But you are right, I mean for horizontal, as long as you don't care, it would not be very useful, let's say. So it's time to look at the special case of vector bundles. Yes. So, in other words, my category C is that of vector spaces, real vector spaces of some fixed dimension with inverted morphisms. And one thing that we wonder now, if we look at this situation, is that the theory that you maybe used of connections or connections on vector bundles as you know them, they will typically take a section of the vector bundle and spit out a section of the same vector bundle. However, here we got some other vector bundle. So, and that's strange, right? But it's not hard actually to relate the things, namely, if you have a vector space, so if, say, W is a vector space, so let me express this in a fancy way, it's an object of this category. Right? And then there's a canonical identification of this space with all its tangent spaces. Then, for any P in W, there is a canonical isomorphism from W to the tangent space at the point P of W. We can always identify the two. And how is the identification? If I have some vector W sitting in here, and this is mapped to what? Well, it depends on how you define tangent spaces, right? And so there are various definitions, and the definition that I prefer is the one given by equivalence classes of curves. And so I have to come up with a curve in this space and take its equivalence class. So what would be the canonical? It should be a curve passing through P, and the direction should have something to do with W. So what would we take? We would take P plus TW, right? So the line through P with the direction W. So that's a curve in this tangent space. And then I take its equivalence class. Now, what's the notation for equivalence classes? Really, in the end, what we did is take this, right? So that's the fancy notation for the equivalence class of curve. It's a derivative point by definition. And if you differentiate this in the classical way, then you get exactly W. So this is the identification. All right, and now we see if so F is a vector bundle, then the vertical space of to the fiber over some point P, let's say the fiber. So that's by definition, that's the tangent space to the fiber over the base point E. So this is how we define it at E. But if we are talking about a vector bundle, then this is a vector space. And so we can use this isomorphism, so let me call this IP. So we can use this isomorphism to identify this tangent space with the vector space itself. So IE in this case, we can identify this with the vector space itself. And now if we do this identification, then what's the fiber of this bundle? S star V at some point P is V at S of P of the fiber FP. Now, what is this? This is by this canonical isomorphism the same thing as this fiber at the base point of this, but the pi of S of P is equal to P. It's just F of P, Fp. So in other words, so it's canonically isomorphic via this canonical isomorphism. And therefore, in this case, you can replace this bundle by the original vector bundle. So can consider nabla X as a section of M in the original vector bundle. If we use this identification of tangent spaces to a vector space with a vector space itself. So this is how we get back to the usual way of covariant derivatives of vector bundles on vector bundles. But for general fiber bundles, this would not have worked because the covariant derivatives really lands in something different, and it lands in something that has a linear structure in contrast to the original model. All right, good. And now, still in the special case of vector bundles, we have this condition that my parallel transport has to be an isomorphism in the category. Now, what does this mean for this category? So still in the special case of vector bundles, this category, P, T1, T2, along C is an element in isomorphisms, the category between the corresponding fibers. What does this mean? It's a linear isomorphism. Exactly. It's a linear isomorphism. So it's a linear isomorphism from f of C1 to f of C2. Let's see T1 to CT2. Yeah, let's see. That's perfectly right. So this now, in the case of vector bundles, it makes sense to ask whether the thing is also linear in S. And I think I get this goal. So let's see what we get. So let's look at nabla x of the sum of two sections, which now makes sense, right? The vector bundle case. So that by this formula, that's the differential of parallel transport of S1 CFT plus S2 CFT, ranging at 0. And now we use the fact that this is a linear map, so we can take this sum apart. So that's the same thing as ddt of, so this is linear, so that's the same thing as S1 CFT plus T S2 CFT. And of course, the differential with respect to t is also linear. So what we get for the first term is nabla x is 1, and for the second one we get nabla x is 2. So that's the additivity. And if we multiply with a function, we can use this formula again. So then we get, by definition, first the parallel transport of, and then I have f of at c of t times s at c of t, differentiated at t equals 0. And I use linearity again of parallel transport. It's linear for each fixed t, so this gives me dt of, and I can drag out this function, f of t times pt at of s of c of t. C of t, yes, thanks. And now let's differentiate this. And here, this is a usual differential in a vector space, so the usual Leibniz rule applies. So I have to differentiate this first term and evaluate the second one at 0. So differentiating the first term gives me a differential of f at c dot of 0 times, and here I have to insert t equals 0. Then this parallel transport gives me the identity, and here I have s of c of 0. Plus, and now I have to, the other term differentiates the second factor, so I have f of c of 0 times, now I have to differentiate this one, but this is just the covariant derivative of s in direction x. So what I have here is df of x times s of p, if p is the base point, plus f of p times nabla xs. So that's the usual Leibniz rule for covariant derivatives. And well, so we could now, so let's see. we saw that nabla xs in this case can be considered as a section in the vector bundle case of the original vector bundle using this identification of tangent spaces to vector spaces with the vector space. And if I leave this slot x open, then I can consider this as a section of cotangent bundle tensor vector bundle, just as before. And these formulas now can be written as, well, nabla S1 plus S2 is the same thing as nabla S1 plus nabla S2. So that's the additivity. And nabla of function times section could now be written as, here we have the differential of f. This is where we insert the vector x. So this is the t star m part times something in my bundle plus, and the second part is just the function f times nabla s. So that would be another way for a shorthand notation for this like this. All right, good. Is that clear so far?
Yeah. I have another little question.
Sure.
Like normally when I know this other approach where you kind of assume on distributions on G principal bundles that the distribution is kind of invariant on the left multiplication. And right multiplication. And so here for vector bundles, could I say something about the distribution, like for example it's invariant under like scalar multiplication or something like that, to like get a C connection then? Like, do I have some...
Okay, so you want to read off this condition directly somehow from the distribution H. Yeah, that's not so clear how to do that. But in fact, this other thing with the principal bundles, this is of course also encoded in this way, right? Because if you have this includes the theory of connections of principal bundles, and then this condition says that the parallel transport must be a G equivalent map, and that's exactly what you need. Yes. Let's become even more special. So this is about vector bundles, but we also have vector bundles with additional structures, which can be encoded by even more refined categories. For example, if we have a vector bundle, a Riemannian vector bundle. So what is the category that we need for Riemannian vector bundles? Vector bundles together with a Riemannian metric. Even more special. Riemannian vector bundles. So F is a Riemannian vector bundle. So this means my category is what? So what are the fibers of a Riemannian vector bundle? What objects are they? They are Euclidean vector spaces. So that's the category of Euclidean vector spaces, let's say of a fixed dimension. And the morphisms were isometries, linear isometries. And yeah, so let's see. So parallel transport. So then this condition means that parallel transport along a curve is a linear isometry. That's what it means in this case. So let's check what this means for the covariant derivative. We have a suspicion already what it might mean. So let's take two sections, S1 and S2, and since we have a metric at each fiber, we can apply this metric. Let me write it with these kind of brackets. We can apply it to get a function, right? And now let me differentiate this function in some direction, x. And And I get another function if x is a vector field, or a number if x is a fixed tangent vector. So let's take a fixed tangent vector. It's again represented by a curve C. Okay, so by this formula, or let's say, not by this formula, but this is, since this is just the derivative of a function, I can write this as the derivative of this function along the curve which represents the vector. So S1 of C of t, S2 of C of t, at t equals 0. And now I use the fact that parallel transport is a linear isometry. So that means I can insert it in the scalar product without changing anything. So that means I can equally well parallel transport the thing to 0. On both sides, doesn't change anything. And now the nice thing is that these are two curves now in a fixed vector space. Namely the fiber over 0, over C of 0. And so I have now a curve in a fixed Euclidean vector space, and there I can apply the usual Leibniz rule for the scalar product. So this is the same as the derivative of the first factor at 0 times the second one underived at 0. So I'm very detailed here, plus the other way around. And so this one thing gives me the connection by this formula from the lemma. This is the covariant derivative applied to S1, and this is the identity. So this is just, that's next to S2, and plus the other way around. So in other words, our covariant derivative is metric, is in the sense of compatible vector connections. Yeah. So therefore, nabla is what one calls a compatible connection or metric connection. But again, this is encoded here in this condition. Okay. Question about this? No. And okay, now let's look at two examples for bundles, which are interesting. The first one is class of examples, really, and the second one is a concrete example. Don't need this anymore. So, example. So let's look at the following situation, namely that my category is given as the category of differentiable manifolds of dimension 0. So what are manifolds of dimension 0? It's a discrete set with a discrete topology, but finite or countable because of this countable base condition for manifolds, right? So these are the objects: finite discrete sets or countable discrete sets. And so now, in other words, we are looking at bundles whose fibers are discrete sets. So such bundles have a common name. C bundle, what is it?
Covering space.
It's a covering. Exactly. So coverings are an example of these fiber bundles with this particularly simple structure category. Now let's see what the theory of connection actually gives us in this case. So these horizontal distributions are complements to the vertical spaces. And the vertical space is now what? What vector space is it? Yeah, only containing 0, because it's a tangent space to a 0-dimensional manifold. So that's a 0 space. And the horizontal distribution has to be a complement there, so there's only one choice. Right? Only one horizontal distribution, namely HE is the complete tangent space to the total space. So there's not much choice in this case. Nevertheless, we can take this one, and now we do have still power transport, right? So for a piecewise smooth curve in the base manifold, so let me have this as C from some compact interval, let's say, to the base manifold. So the parallel transport still exists. It exists, the fibers, in this case, there's no issue with the existence of parallel transport. So it maps the fiber over C of A to the fiber over C of B. And it has a name. Does anyone know what the name is for this? So let's say, at least in the case that it's a closed curve. So let me restrict to closed curves now. Closed piecewise smooth curve. So that means C of A is equal to C of B. And let me call this point P. And then the parallel transport maps actually the fiber over P to the fiber over P, right, to itself. And this has a name in the covering theory. Does anyone know what this is called? Yeah, it's the monodromy. It's the monodromy of this curve, right? So let's call it, let me just have the monodromy. And so let's see how this looks in a particular example. So for instance, an example of the example. So if we look at model fiber Z, total space, so that's the total space R and the base manifold S1, the usual standard example of a covering, where the projection map from R to S1 is given by pi of t equals e to the pi by t. So I'm considering this as a subset of complex numbers. So let's see. So we have this usual, so that's S1, the base manifold, and here we have our real line going up and down, and the projection is this projection, so that's basically how it looks. And now let's just recall how we defined parallel transport. So I have to make a choice for the base of the curve. So let's take a curve which goes around the circle once. So let me use a curve from the unit interval to S1 by going around once. So this would be given exactly by the same formula as here, e to the pi t, right? So that would be my curve. So how did we define parallel transport? So we said we pull back the bundle. So then we pull it back to this unit interval. And now what's the pull back bundle in this case? To each point of the interval, we associate the fiber of the corresponding image point, right? So in particular, since 0 and 1 map to the same point, they get the same fibers here. So so these are, that would be the fiber over the point P. So these are the same over 0 and 1. And now over other points, somehow this moves. And really, if you go go around once, then you move up one's door. So really, the total space looks like this. And if you now take the standard vector field here, you lift horizontally and you follow the flow lines, it just means that you follow these curves. So that means if you apply your parallel transport, you just move up one floor. So that would means that along this curve from 0 to 1, and you apply it to some element in the fiber really is Z. Yeah, these are the fiber for t equals 0 and t equals 1. So to emphasize this, let me call it k like an integer. And then this will just be given by k plus 1. So that's the parallel transport in this case, and that's also, of course, the monodromy action for this curve, just moving up by one in this example. Good. Okay. So that's the special case. All right. And now another example, which will also be of importance later, when we really treat characteristic classes. And example, that's now a true example. The base manifold will be complex projective space. Remember, as a set, this is just the set of lines, right? Of complex lines. L and C, n plus 1, where this is a one-dimensional C vector subspace. All complex lines, they form a complex projective space. So that's a vector bundle. So here the category would be vect, or the complex numbers, dimension 1, or even verticalize morphisms, let's say. So that's my category. And well, now I want to give you a really nice vector bundle over it, namely the bundle F at the point L. So it should be a vector bundle over CPN. Points of CPN are these lines. How about just taking that line? All right. So to each point, I associate itself, because the point is a line. So that is at least a vector pre-bundle, definitely. So it's for this category, it's certainly a pre-bundle. And I claim that this is a true vector bundle. And in order to check this, what would I have to do? That it's not just a pre-bundle, but an actual bundle. So what do I have to do? So what do we need for a bundle in addition? Yeah, smooth atlas of what? Of local trivializations. So we need local trivializations such that the transition maps between them are smooth, right? We need a C-infinity atlas of local trivializations exactly. And how can we get them? Well, actually, we get them pretty much in the same way that as we constructed coordinates on this thing to prove that it's a manifold in the first place. I did it for real projective space, but for complex projective space, the procedure is exactly the same, just looking at complex maps rather than real maps. So let me explain how this can be done. So how we can get local trivializations for this. So atlas of local trivializations. So how did we construct coordinates on complex projective space? So we first constructed coordinates and then we checked that this is actually manifold, so by this general criterion. And how did we do that? Well, we were looking at affine codimension 1 hyperplanes in Cn+1, and so, only such that do not contain the origin. And then we looked at intersection points of these lines. So that alpha from Cn to Cn+1 be an affine linear embedding such that the origin is not contained in the image, in this hyperplane. And then the coordinates were defined on the set U alpha of L's in CPN for which intersect this hyperplane. For which this is non-empty. So we removed all the ones which are parallel to the hyperplane. And in fact, in this case, this intersection point is unique. So that's a unique point, this intersection point. And yes, so that's what we did. And then we constructed coordinates for the L using this affine connection, basically taking the coordinates coming from Cn. Right? So L leads to a unique intersection point, and then you look at the vector which you need to map under alpha to this intersection point, and these are the coordinates of L. So that was the procedure. And local trivializations can now be done similarly. So we want to define a local trivialization over U alpha. So this should give me an item for each L in U alpha. I construct a corresponding local trivialization over U alpha, and this should give me an isomorphism from the fiber over L, which is L, right? Which is the same thing as L, to the model fiber. And the model fiber here, one-dimensional complex vector space, is just C itself. So that's what I need, right? An isomorphism. And I do this, it's simpler to write down the inverse of it. We have phi L to the -1 of a complex number set is equal to. Now I need to map this to some point to some point in this line. And what can I take? Well, I have this unique point in the line given by this intersection, and I just take z times this point. Let me write it like this: z times this intersection point. So actually, it's a set containing the intersection point, but you know what I mean. Yeah? So this is a point in the line, and so every other point in the line is a unique multiple of that point. And the coefficient that I need is my z. So that's an isomorphism between these two one-dimensional vector spaces. So that's what I use. This is the canonical thing to do. So this gives me definitely a local trivialization, and now what one has to check is that they are C infinity compatible, any two such. If I take another affine embedding, I get another local trivialization, and then over the common domain of them, they must be C infinity compatible, right? So for another such embedding, we call it beta. So obtain another local trivialization, call it phi L, also again from FL, which is L, to C. And now I have to look at the transformation map and see that this is smooth. one has to look at the map from U alpha intersect U beta to the isomorphisms of the model fiber. Okay, so let me write it down in a fancy way first. The isomorphisms in this category of the model fiber, but what are the isomorphisms? They are linear isomorphisms, but linear isomorphisms from C to C are just given by multiplication with a non-trivial complex number. So I can identify this with C star, right? So these are the transition maps, and so what is the map? It's you first apply phi L to the inverse, and then you compose it with phi tilde L. So, and you map, what did we say? You map L in this intersection to phi L inverse composed with phi L tilde. So what does this mean? Here's the formula for phi L inverse. So you take the complex number in C star, you map this to Z times this intersection point. So that's a point in the line L. And now you take this point in L and you look at the intersection of L with the other affine plane, hyperplane, beta of Cn, and you check what the coefficient is that you get to that intersection point. So L times this intersection point has to, Z times this intersection point has to be rewritten as Z tilde times the other intersection point. And now the question is, how does Z tilde depend on Z? Yeah? It depends, this of course depends on the choice of alpha and beta, but it also depends on L. So this is then given by, if I use this identification, by some multiplication of a non-trivial line, a non-trivial complex number, which somehow depends on this line, choice of line. The question is, how does this depend on the line? And if you compute it, and we did it essentially when we computed the transformation maps here to check that the coordinate transformations are smooth, then it turns out that this map, if you express this in the coordinates that we introduced, that they are a rational function. In coordinates induced, coordinates on CPN, induced by this embedding alpha, the map L maps to Z of L is a rational map, a rational function. There's no point in computing the precise formula for it. It's easy to do. It really doesn't matter. The only thing that really matters is that it's smooth. So in particular, it's smooth. And so this means that I have obtained a C infinity atlas of local trivializations, namely all those local trivializations which are induced by such embeddings. Maybe I should have called this thing phi alpha L, and then I have written down the inverse here, and then this would not have been phi tilde, but rather phi beta L, and then I would have had phi beta L to the minus 1, and maybe the other way around, doesn't matter really. Beta L, and yes. So, therefore, the set A of all phi alpha, where alpha is such an embedding, of a linear embedding, not containing 0. So that is a C infinity atlas of local trivializations for my bundle F. And since the bundle is such that it maps L to itself as a tautological construction, and that's why it's called the tautological line bundle over complex projective space. It's called the tautological line bundle or vector bundle of rank 1. Such things are usually called line bundles. CP. Question is the tautological line bundle trivial? Here we wrote down an atlas of global trivialization, but maybe there exists a global trivialization, or maybe not. Answer will be given later. At the moment we cannot answer it yet. I could try to find a global trivialization, but I really don't know how to do it, so no idea. So we'll see later. Good. So that's the tautological line bundle, and this is related to another thing, which is pretty famous, and which can be obtained from the tautological line bundle as follows. So let's modify the bundle a bit. So rather than taking as a fiber the whole line, we only take the unit vectors in the line, okay? So we define a new bundle, FL, F1L, which is obtained as saying we'll not take the whole line, but only the unit vectors in the line. This makes sense because these lines are subsets of Cn plus 1, so they come with a canonical scalar product and norm. So we take all those vectors C in L for which the norm is equal to 1. It's a subset. So, and well, certainly no longer a vector bundle. So what kind of a bundle do we get here? Well, if we have a line, so that's a complex plane, a plane in the real world, right? And we look at all points that have constant length 1. So that's like in the complex plane, you look at all points of their own complex numbers of length 1. So it's a circle, right? So that is a circle. And in fact, there is an action on that circle by the unitary group. So let me put my Lie group is going to be the unitary group of 1 by 1 matrices. Unitary, what are these? Well, these are all complex numbers, omega. So these are vectors, the z's are vectors, but the omega is a number of length 1. Or 1 by 1 matrix containing this complex number. And there's an action now. G acts on F1L by multiplication. If I have a unit length vector and in Cn plus 1 and I multiply with a unit complex number, I get another unit length vector. And it's certainly the same line because it's a multiple. So in other words, G acts on all these particular circles by, so G, or rather it was called omega here, by omega, and Z is being mapped to what? Omega times Z. But that's not exactly what I want. I want to have a right action because I want to get a principal bundle. This would be a left action, so let me invert this one to turn this into a right action. And this we can then define to be that the right multiplication of omega. So this is the definition of that dot. Okay, yeah, it's commutative, that's true. Okay, then you're right, yeah, we don't really have to do it. But for any other group which is not, we would have to do that, yeah. Okay, yeah, you're right. Okay, but that's even simpler. And good. Now we have this, and this action is simply transitive. So we just have to recall what that means. What does it mean? Simply transitive means if you have any 2 points in this set, then there is a unique element in G mapping the first one to the second one. So that means any 2 unit vectors in this line, there's a unique complex number omega of length 1 that I get with which I have to multiply to move the first one to the second. And that's obviously true, yeah? So action is simply transitive. So this way we obtain a U1 principal bundle. F1 on my complex projective space. By starting from the tautological light bundle and then restrict myself to only unit vectors. U1 principal bundle. Okay, now what's the total space of this? So the base manifold is CPN. The model fiber. So the model fiber F1 is just S1. Right, they're all diffeomorphic to S1. And or U1 if you like. And what's the total space? Well, we can write F1L as follows. It's a set of all points in L which have length 1. So I can write this as the intersection of L with the unit sphere. And it's the unit sphere in Cn plus 1. Cn plus 1 is the same as R2n plus 2. So it's the unit sphere 2n plus 1. A unit sphere in R2n plus 2. So I can also write it like this. And now, indeed, so let's see. Every element in the unit sphere is certainly in some line. Just take the line generated by this vector. But all the lines, these lines, or these intersections, are mutually disjoint. Because if 2 lines have an intersection, they coincide. So, in other words, the total space of this bundle, which is the disjoint union of all these intersections, just gives me S2n plus 1. So it's a disjoint by definition, is a disjoint union for all lines in CPN of these intersections. But they are all disjoint, so it's just the union, and the union gives me S2n plus 1. So that's the total space. So we have a bundle with total space S2n plus 1, with base manifold CPN, and with fiber S1. And this bundle is called the Hopf fibration. Okay. F1 is called the Hopf fibration. Sometimes this name is used especially for the case when n is equal to 1, because when n is equal to 1, then the fiber is S1, the total space is S3, and the base manifold is CP1, but CP1 as a manifold is S2. So it's a fibration with base manifold S2, total space S3, and fiber S1. in the case n equals 1. Well, technically, we would also have to check that it's not just a pre-bundle, but an actual bundle. So we would try to take the trivializations of the tautological line bundle to turn them into trivializations of this one. And then, once you have that, you only need to show that these trivializations map the product of U alpha cross S1 diffeomorphically onto the corresponding part of the total space. And you would write it down directly as a map to that and check that this is the case. Yeah, that's true. Yeah, it's right. I mean, it's not correct to just have this in a set theoretic sense. But you certainly believe that it's correct. Okay, so that's the Hopf fibration. And, well, let me give you a connection on it. We have, connections on all kinds of bundles, in particular also on principal bundles. And let me give you a connection on it. For this, we have to identify our vertical space and that sort of thing. And it's convenient in this particular case because everything embeds into Cn plus 1, so we can work with subspaces of Cn plus 1. So first of all, if I take the tangent space of the total space, which is S to n plus 1 at some point, so Z is now a unit vector in this sphere. So, well, the unit, so that's S to n plus 1. And the units, the tangent space to the unit sphere in some Rn is easily characterized as a subspace. Namely how? So the point is Z, and it's the orthogonal complement. But we have to be careful, it's the real orthogonal complement. We have two orthogonal complements here, right? We have the complex orthogonal complement with respect to the Hermitian metric, and the one for R for the real R2 n plus 2, and we have to take the real orthogonal complement here. Yes, that's correct. Now, the tangent space to a fiber, so let's write like this, FL at some point Z, which is just the tangent space to the fiber itself, but the fiber is a linear space, so I can again canonically identify this with L itself. It's also a subspace, so all this sits in Cn plus 1, right? And finally, so that's for the tautological bundle. And for the Hopf fibration, I have to intersect with this sphere, tangent space of F1L. So that's the tangent space of the intersection of L with that. And so this gives me, tangent vectors are represented by curves in this intersection, so they are the curves in L and also in the sphere. So they have to satisfy both conditions. They have to lie in the orthogonal complement and also in L. So this is the intersection of L, canonically isomorphic to the intersection of L with the real orthogonal complement here, again as a subspace of Cn plus 1. So that's what we get here. So here the real dimension of this thing is equal to 1, because Z is in L. And so we take the orthogonal complement of a complex point in a complex plane with respect to real scalar product. So we are left with a real line sitting in this complex line. But it should be, because the fibers are one-dimensional. Okay, good. And so what do I take for my connection, for my horizontal distribution? The canonical thing to do is to take the complex orthogonal complement. So let's see why. The complex orthogonal complement is certainly contained in the real complex orthogonal complement. So the HC is contained in this tangent space. That's good. So if we look at HZ, or let me say, if we look at this space and at this space. So first of all, do they have a non-trivial? So what's the intersection? The intersection, so if something is in here, then it's in L, but it's also in the orthogonal complement to the point. And so since that point generates the whole complex line as a complex vector space, it will be in the complex orthogonal complement of the whole line L, and so it will be 0. So the intersection of these two is trivial. And now they have the right dimensions. So this is one-dimensional from the real point of view, and this one is 2n-dimensional from the real point of view. Both spaces are contained in this space, and therefore they form a direct sum because of this. And both spaces are contained in that space. So that this one is the vertical space. This one is what I use to define horizontal space, and this one is the complete tension space, the total space. In other words, it's a horizontal distribution, right? So it's a horizontal distribution. Now, in this case, you don't have to ask whether parallel transport exists because we have compact fibers. Okay? So, compact fibers. Therefore, parallel transport always exists, the one which is related to this distribution, or any other horizontal distribution. Well, that's something we need if you want to talk about a connection. And, well, then you can also check that the parallel transport, maybe I come back to this next time, parallel transport, the induced parallel transport, P, T1, T2 along any line, is actually U1 equivariant. You can think about this until next time, which means that it's actually what it should be, namely an isomorphism in my category of G of U1 equivariant of U1 simply transitive manifolds from between the corresponding fibers. In other words, that is really a connection as a principal bundle. It's a principal bundle connection on this particular principal bundle, the Hopf fibration. Okay, so my time is up anyway. I'm over time already. Sorry for that. But I didn't want to break this discussion into two parts. Thanks for your attention.